Hi, this is Alfawzia Nihar from At Home Tuition. Welcome to our session today. The topic that we are going to discuss in our today's video is Union, Intersection and Complement of Events in Probability Part 3. Complement of an event. In statistics, the complement rule is a theorem that provides a connection between the probability of an event and the probability of the complement of the event in such a way that if we know one of these probabilities, then we will automatically know the other one. Yes, in today's video we are going to concentrate only on the complement of an event. The complement rule comes in handy when we calculate certain probabilities. Many times the probability of an event is messy or a little bit complicated to compute, whereas the probability of its complement is much simpler compared to the probability of any event. Let us start with the statement of the complement rule. Before we see how the complement rule is used, we will define specifically what this rule is. We begin with a bit of notation. The complement of an event is denoted by A dash or A raised to C. The C mentioned here is denoting the word complement. The complement of an event A consisting of all the elements in the sample space S that are not the elements of set A. It is denoted by AC or A complement, the A dash. Okay. The complement rule is stated as the sum of the probability of an event and the probability of its complement. Sum of these two will be equal to 1, as it can be expressed in the equation format. Just subtract probability of A from both the sides of the equation, you will get an equation in terms of probability of A complement. Does this make sense to you? In some cases, we will find the probability of A by using the formula 1 minus probability of A dash or A complement. Both are same. We are just rewriting the formula probability of A plus probability of A complement equal to 1. Okay, let me take few examples that will show how to use the complement rule. Okay, it is after seeing the example problems, you will understand that this theorem will both speed up and simplify the probability calculations. Here is the example. Imagine that you have two six-sided number cubes that are rolled, or you can also imagine dice, a pair of dice. Find the probability that the sum of the numbers rolled is less than or equal to 3. Find the probability that the sum of the numbers rolled is greater than 3. Okay. As a first step, all we have to do is to identify the sample space. Sample space means a set which consists of all the possible outcomes. Here we are going to imagine a 2 die or 2 number cubes, and each number cube has 6 possible outcomes. Do you agree with me? Okay. So how can we list out the 6 total possible outcomes? For each of the cube, the possible outcome is 6. So by using the multiplication principle, we find that totally there are 36 possible outcomes. For example, 1 and 1 represent the 1 rolled on each number cube. Here is the list of possible outcomes. So 1, 1, 2, 1. So these are the outcomes, these are the combinations. If you count, you can see that there are totally 36 outcomes. Okay. Now read the part A question. Find the probability that the number of sum of the numbers rolled is less than or equal to 3. So from this list, identify the numbers, the sets that will give you a total of less than or equal to 3. Okay, I'll also list out the total sum here. For the same outcome, 1, 1 total is 2, 2, 1 total, if you add these two, 2 plus 1 is 3. Hope you understand this list. Okay, in this list, 1, 1, 1, 2, 2, 1 are the outcomes that are less than or equal to 3. Am I right? So there are 3 out of 36. If you simplify this, you'll be getting 1 over 12. That's it for part A. Does this make sense to you? Okay. Part 2 question asks us to find the probability that the sum of the numbers rolled is greater than 3. So read the question carefully. So all the results except these 3 are the answers for the probability of second question. Am I right? In this problem, we have only 36 outcomes. So it is somewhat easy for us to calculate the outcome. But I'm going to show you the same answer using complement rule. So let's see how it reduces the time for calculation. Rather than listing all the possibilities, we can use the complement rule because we have already found the probability of this event in part A. And now we are going to find the probability of the complement of that event. In first case, It is the probability of less than equal to. In second case, probability of greater than. So instead writing as a statement, let me take this event as E, complement of sum of less than or equal to 3. We know the complement rule. Probability of some event, complement of some event is nothing but 1 minus probability of that event, which is nothing but part A answer. So 1 minus 1 over 12. So this is going to be 11 over 12. Hope you're clear with this example. In case if you're doing like the normal probability, you have to count all the possible outcomes. In this case, it is possible for you because only 36 outcomes are there. In some cases, in some problems, the outcomes would be too large. It would take so much time to calculate. In that cases, this application of complement of rule will help you to save so much time and make your calculation work easy. Let us also see one example in finding the probability without the complement rule. Here is the example. Suppose that we flip 8 fair coins, and what is the probability that we have at least one head showing? So for this example, one way to figure this out is to calculate the following probabilities. And the denominator of each is explained by the fact that 2 raised to 8. Am I right? So I'm going to use the formula for the total possible outcome, 2 raised to n. Here n is flipping 8 fair coins. So 2 raised to 8 is 256 outcomes. Do you think listing out all the 256 outcomes is easy? And in this case, each of them are equally likely event. So I'm going to use the formula for combinations here. Probability of flipping exactly one head. I'm going to start from 1. It is combination of 8, 1 over 256. You could either apply the formula and solve it manually, or in case if you're allowed to use the calculator, you can use it. So I'm getting 8 over 256. Find the probability of flipping exactly 2 heads. Same way you have to list out for all the 8 heads. 1 head, 2 head, 3 heads, till 8 heads. By using the combinations formula and dividing it by 256, I'm getting 28 over 256. Probability of flipping exactly 3 heads is 8, 3. Combination of 8, 3, 256, which is nothing but 56 over 256. And for this one, 4 heads. Probability of flipping exactly 4 heads is combinations 8, 4 over 256, which is 70 over 256. So this is the probability for exactly 5 heads and exactly 6 heads. Likewise, the probability of flipping exactly 7 heads would give you 8 over 256. You can also check these answers by solving by yourself. And these are mutually exclusive events. So we sum the probabilities together using the one appropriate addition rule. So what does that mean? It means the probability that we have at least one head is, if I add all these, I get, and add and subtract, I get 255 out of 256. Did you notice that without using the complement rule, how difficult and time consuming this example took us? Yes. So if you use the complement rule, it will save so much time and avoid these calculation steps. Okay. So this is how we use the complement rule to simplify the probability problems. Okay, we now calculate the same probability by using the complement rule and see how it will work out. The complement of an event, we flip at least one head, is the event there are no heads. Am I right? Okay, there is one way for this to occur, giving us the probability of 1 over 256. I'm going to use the complement rule and I'm going to find out our desired probability. That is 1 minus 1 out of 256. Just apply the formula and plug in the value. Probability of there are no heads. So 1 minus probability of there are no heads. And if I substitute all this and do the fraction subtraction, I'm getting 255 out of 256. This example demonstrates not only the usefulness but also the power of the complement rule. Although there is nothing wrong with the original calculation, it was quite involved and required multiple steps. But in contrast, we used the complement rule for this problem. There were not as many steps where calculation could go awry. So the complement of an event is all the other outcomes, not the ones we want. And together the event and its complement makes all the possible outcomes. It is sometimes easier to work out the complement first. Sometimes it is easier to work out the event first. So choose accordingly. So you have to work out the problems according to the method, to the way that saves so much time. So please keep this in mind. When you're looking at an event that's fairly complicated, you always prefer finding the probability of the complement first rather than finding the probability of that event. So a small recap on the definition of the complement of event. The complement of an event A is the set of all outcomes in the sample space that are not included in the outcomes of event A. Hope you're clear with this concept. In case if you get any query regarding the complement of event in probability, please let me know. See you in the next video.